Hello everyone, my name is Mengchen Huang, a graduate student in Dr. Jeremy Levis Group at the University of Pittsburgh and Pittsburgh Quantum Institute. Today I'm going to talk about our research project studying anisotropic superconductivity of nanowires at 110 LaSTO heterointerface. This work is collaborated with Dr. Mengchen and Dr. Arandu's group at National University of Singapore. Recently, an unexpected conducting interface has been reported in the 110 LaSTO interface. There is no polar discontinuity across the 110 case, as we can see in this figure. In the regular 001 LaSTO interface, there is a polar discontinuity, but although there is no polar discontinuity, there is still a critical thickness for the 110 LaSTO interface, which is 4 in the cell. Above it, the interface is conducting. Below it, the interface is insulating. And anisotropic sheet resistance has been reported in the 110 case, which is attributed to the anisotropic atomic arrangement along the 001 and 1-10 direction. And recently, researchers started to investigate the superconductivity in the 110 case and compare it with the 001 case. And a recent archival paper reported the observation of quantum Griffith singularity in the 110 LaSTO interface. So considering the anisotropic sheet resistance and also superconductivity in the 110 case, we want to ask this question: is there anisotropic superconductivity along different orientations in the 110 case? And we think if we can make 1D nanowires along the 001 and 1-10 direction, they can be good study platforms. And the broader question is, what will be the 1D transport properties of the nanowires in the 110 LaSTO interface? And are there any difference compared to the 001 case? And what this difference will tell us about the LaSTO systems. So to answer these questions, we use 3-unit cell 110 LaSTO, which is insulating, and we pattern the sample along certain crystal orientations, and then use the conductive AFM lithography to create nanowires along the two different crystal orientations. Basically, the conductive AFM lithography works similar to the 001 case. We use positively biased tip to make nanowires, one along the 1-10 direction, and the other is along the 001 direction. And after making these two nanowires, we write two more nanowires as the voltage probe to measure the 4-terminal differential resistance. So here is a schematic for our device and measurement. Basically, we can source current between electrode 1 and 6, and then measure the 4-terminal voltage drop between electrode 2 and 3, which is along the 001 direction, and also between the electrode 4 and 5, which is along the 1-10 direction. And after making the device, we cool it down to base temperature, which is 50 mK, and then we measure and plot the 4-terminal differential resistance as a function of temperature and the source bias. In the intensity graph, we see the superconductivity terms, one for the 001 direction and the other for the 1-10 direction. And we can also plot out the 4-terminal differential resistance versus temperature around zero bias. Basically, we see a broad superconductivity transition as a function of temperature, and also the 1-10 nanowires has a higher residual resistance compared to the 001 case, which shows some anisotropic behavior. We can also turn on the external magnetic field and sweep the temperature at a certain external magnetic field. So here again, we plot out the 4-terminal differential resistance versus temperature near zero bias under different magnetic field, and we can see as the outer plane magnetic field get higher, the superconductivity transition disappears, and also the upper critical field is different for the 001 and 1-10 1,0 case. So to look at the magnetic field dependence in more details, we can fix the temperature at 70 mK and sweep the external magnetic field while measuring the 4-terminal differential resistance. Here we plot out the intensity graph of the 4-terminal differential resistance as a function of magnetic field and the source bias. Again, we see the two superconductivity domes, and we can clearly see the upper critical field is different for the 001 and 1-10 case. We can also study the transport as a function of backgate voltage for the 1-10 and the 001 directions using these nanowire devices. So basically, from left to right and from top to bottom, we decrease the backgate voltage and plot out the normalized differential resistance as a function of magnetic field and source bias. So basically, in both directions, as we decrease the backgate voltage, the superconductivity first gets stronger, and after certain backgate voltage, the superconductivity gets weaker and finally disappears for both directions, leaving a high resistance state around zero bias. Although the trend is similar in both directions, the exact number of the backgate voltage where the superconductivity is the strongest is different for the two directions. So to quantify the critical field dependence on backgate voltage, we can extract the upper critical magnetic field from the intensity data and we plot it out as a function of backgate voltage. So basically, we see these two superconductivity domes, and the peak of the two domes has a backgate voltage shift. We can also make a nanowire device with more nanowire sections. We add, besides the 1-10 and the 001 oriented nanowires, we added 2 more nanowires which are 45 degree rotated. And again, we can measure and plot out the upper critical magnetic field as a function of backgate voltage. So basically, again, we see 4 domes for these 4 directions, and the superconductivity domes between 001 and the 1-10 directions has a shift. There is no shift between the 2 45 degree rotated nanowires, which is consistent with symmetry consideration. And we think the possible explanations for the superconductivity dome shift for the 2 directions is related to the leaf-sheet transition and also the band structures. Leaf-sheet transition has already been reported in the 001 LaAlO3 interface. Basically, when the carrier density is low, electrons only occupy the dxy band, and if we increase the carrier density by increasing the backgate voltage, new bands like the dx divisor bands of different symmetry will be occupied. So the leaf-sheet transition is a transition from a 1-band model to a 2-band model, or from a 1-band to a new band with different symmetry. So basically, there is a correlation between the superconductivity of the leaf-sheet transition critical density. As we can see here, the superconductivity dome peaks has the same backgate voltage corresponding to the critical density for the leaf-sheet transition. The band structure is also important for these possible explanations. In the 110 case, the lowest energy band is dx divisor band, but in the regular 001 case, the lowest energy band is the dxy band. Besides this difference, we are studying 1D nanowires along the 2 directions. It is important to understand what are the band structures of the 1D nanowires along 001 and 1-10 directions. They are probably anisotropic due to the anisotropic atom arrangement, and probably there is a different critical density for the leaf-sheet transition for the quasi-1D nanowires. That's why there is a superconductivity dome shift between these 2 nanowires. So the summary, we observed anisotropic superconductivity of nanowires at 1 LaSTO interface, and there is a superconductivity dome shift between nanowires along 001 and 1-10 directions, and we think the dome shift is related to the current density and also related to the band structure and also the leaf shear transition.